Hello everyone. So this is our 10th session on the study guide in the organic retrosynthesis, and we are basically uh, already discussed several examples on this retrosynthesis. So as we are right currently working on the some retrosynthesis of this material which involve the chiral center, and that we are discussing from the last few sessions. So before moving to the session, I would like to uh, ask you, do you have any doubt regarding whatever the content that are covered by the professor in this course up to now? So if you have any doubt, please let me know, or else we'll start our some problem based on this asymmetric synthesis. So if you have any doubt, please let me know. So you can also use the chat box if you have any doubt. So okay, so as we are discussing the asymmetric synthesis and the and also have already covered why this asymmetric synthesis is important, mainly because of these some of the natural products and the active pharmaceutical ingredients which involve the chiral centers. So it is important to have this compound in the form of enantiomer pure form. Uh, so we have already discussed the three important method. So among them, the first one is the resolution. So the resolution, we generally focus on the purification of these final compound. So depend upon the whatever isomer we are getting in the reaction mixture reaction. So let's say in this example we are getting R and S, both are isomers, enantiomers. However, they are inseparable. So what we can do in the resolution method? So we can make this is one of the approach in the resolution method. We can add external additive, and so in this case, this external additive has been added to the this mixture of R and S enantiomer. So after adding this additive, what happened? One of the enantiomer get crystallized. However, another enantiomer remain soluble in the solvent. And if you do the filtration, so the crystalline one which go we can separate from the soluble one, right? So this is how by this using this approach we can basically separate the two enantiomers from each other. So in this case, so from A to we can get the mixture of B and both two enantiomers. However, from this yeah, from this mixture, by using this resolution technique, so we can basically separate these both from each other. Generally, enantiomers are inseparable from each other, but by using this resolution method, by just in this case by addition of the additive, we can basically get the two of the enantiomer separated from each other. Another method is the chiral pool synthesis. So what we can do in this chiral pool synthesis is basically we select the some of the starting material in such a way that so we can carry forward that chiral center till the end of our product. So what happened? So this is the one example here you can see. So in this example, you can see what we have did in the synthesis of this L-lysine molecule. So this is L-lysine. This is our target molecule. So this is our target molecule. So what we have did, we have selected a L-serine as our starting material, and the chiral center of this L-serine we kept till the end of our synthesis. So in this product, you can see the same chiral center will be remain as it is. So this chiral pool synthesis of essential amino acid L-lysine from the naturally non-essential amino acid that is the L-serine can be achieved. So in this case, you can see the in this synthesis. So L-serine taken, then we did the CVZ protection of this L amine group, followed by the esterification by using this benzyl alcohol and the coupling reagent DCC here used. Further, if we do the PCC oxidation, this oxidation stop at the aldehyde stage from this primary alcohol. So we stop this oxidation of this primary alcohol to the aldehyde stage. And once this aldehyde we got, so this from this aldehyde, so what we did, we the aldehyde coupled with this ylide under Wittig reaction condition. So what happened? So with the ylide, so we get the alkene as a product. So once we get this alkene uh, uh, from this Wittig reaction, if you do the just H2PDC reduction, we get this L-serine as our final target molecule. So in this case, you can see H2PDC reduction in the one step. What happened? The olefin reduction step also occurs, and followed also the CBZ reproduction step also occur in the same reaction condition. So this is one of the very good example in which two steps we can achieve in this one reaction condition, right? So anyway, this is our final target molecule L-lysine, and you can, if you look at the chiral center present in the L-lysine, so that chiral center was actually comes from the starting material that we have used for this L-serine, right? So this is the chiral pool synthesis. And the third important asymmetric synthesis method that we have seen. So this is again example of the chiral pool synthesis. You can have a look. I will directly move to the another method, which is the third one is the chiral auxiliary method. So we have already discussed all these method in the last video. So I just kind of recap, so as it will be easy for you guys to understand some of the problems based on this uh, asymmetric synthesis. So the third important approach is the chiral auxiliary. So what happened in the chiral auxiliary? We select some functional group, some added adduct. We can introduce that part into our starting material. So in this case example, we have the propanoic acid. Our target molecule was this R2 methyl 3 phenyl propanoic acid. So how we can synthesize this target molecule? So for that, what approach here used is the chiral auxiliary approach. So starting from the propanoic acid, what we did the acylation, sorry, the created this propanoic acid with the PCl5. What happened? Acid converted into acyl chloride, and once this acyl chloride is formed, couple this acyl chloride with this chiral auxiliary. So this is the chiral auxiliary. So this chiral auxiliary and the acyl chloride, what happen? This chiral auxiliary get attached to this carbonyl center, right? Once this auxiliary is attached, now when you do the LDA, when it treated this compound with the LDA, that is lithium disulfide amide, so which is strong base. So it abstracts this proton and it forms the Z enolate as a major product. Why? Because of this steric hindrance because of present in the chiral auxiliary part. Uh, Forced to form a Z enolate as a major product. And once this Z enolate is formed, when it treated with this Z enolate with the PHCH2I, that is aryl iodide. So not aryl iodide, it is alkyl iodide actually, phenyl substituted. So when you treated with this this iodide, what happened? This CH2 pH is get attached in such a way that, so to avoid the steric hindrance, so this pH CH2 pH attached from the opposite side to the steric bulk present in the auxiliary part, right? So basically we get the major product in this one. So in which you can see this CH2 pH is directing downward. However, this bulkier group was present in the directing upward. So basically we are getting this product as a major product, right? And upon removal, how to remove this? So just now we don't want this chiral auxiliary part in our target molecule. So we can, at last step, what we can do, we can just remove this chiral auxiliary from the our intermediate. So once this intermediate form, what we can do, we can treat this with the lithium hydroxide and H2O2. So this particular chiral auxiliary can be removed from our target molecule, and we get our target molecule here. So you can see So this approach is called as a chiral auxiliary approach. So what we have did basically, we have added some auxiliary into our starting material in our into our starting material. So that auxiliary induced the uh, one of the enantiomer formation of one of the enantiomer in the major form and one in the minor form. So basically, the in this case, what happens, the steric hindrance present in this auxiliary part helps to form the only selectively Z enolate. Also, in the second step, also the same steric hindrance makes it is impossible for this incoming electrophile towards this carbon center. So from the side on which the chiral auxiliary attached, it is difficult for the electrophile to come close towards this reaction center. So what happened? The majority of the electrophile comes from the opposite side to the chiral auxiliary part, and we get the here selectively, not we get some sort of selectivity in this reaction. Basically, here we get some sort of enantiomer selectivity because of this chiral auxiliary. So this is how this chiral auxiliary work. So these are all the examples of the different approaches used in the asymmetric synthesis. Let's move to the, this is the same another example. As you can see, it's same based on the chiral auxiliary approach. This example I have already discussed in the last session. So I will not go into much detail, but here you can see the similar chiral auxiliary has been introduced to the starting material. And once this auxiliary introduced into starting material, further uh, the same in from in this step you can see particularly. So this from this intermediate to this product, what happened? The alkylation step occurs at the alpha uh, position of this carbonyl compound. Particularly here it is amide. So alpha position of this amide, the alkylation step. Without chiral auxiliary, this alkylation step occur in the random manner. We get both the product in which this CH2 CH3 group attached either from top side or either from bottom side. So we get basically racemic mixture in the product. But if you introduce this chiral auxiliary, what happens? The steric bulk present in the chiral auxiliary doesn't allow this approaching electrophile from the side of this chiral auxiliary. So in this chiral auxiliary, you can see this bulkier group create a steric hindrance from the back side. You can see here. So this bulkier group makes the steric hindrance from the back side and allow only electrophile to come from the top side. So we get the major product in which this electrophile is attached to this compound from the top side. And at the last, we can basically uh, remove the uh, auxiliary part and we get this intermediate. So our target was further one step away. So what we did last step, they treated with this acid with the ammonia and we get this our final target molecule. So this is another approach, that is the chiral auxiliary approach. So we have now the toolkit for our retrosynthesis. Now let's take some examples of the retrosynthesis. So if you guys have any doubt, please let me know. We'll uh, take some question if you have any question or doubt. So we can discuss that one right now. So do you guys have any doubt regarding the this asymmetric synthesis? Because now we are gonna take some questions which involve this type of asymmetric synthesis. We'll take some simple question first and then start slowly to the some difficult one. So let's take the first example here. So here, this is the example in which you can see here. So this is what the target molecule was now, and this is the starting material. So basically, which reaction this one is? This one is the aldol condensation reaction. So we have the alpha protons to this carbonyl group. When it reacted this with this acid, what happened? It formed initially the imine intermediate. So we can see. So this imine intermediate ketone plus amine, it forms the imine, right? So this imine, once this imine is formed, so we have here this nitrogen get the positive charge because uh, this become tetravalent. So this proton is now it convert into the enolate form. Sorry, enamine. This was the imine. So this is what convert. Now nitrogen has the lone pair. So what happened? So when it react with this aldehyde, so this nucleophilic lone pair goes here and this bond attacks on this compound. So in this step, what happened? Because this methyl group is present on the top side, so this attacks from the top side is somewhat sterically hindered, and therefore we get some uh, enantioselectivity in this step. And later, what we can do? So basically, once this attack takes place, so what happen? The intermediate we get here is this one. So the attack on this oxygen takes place. So we get attack or takes place on the oxygen from the back side. So OH comes on the front side. So this methyl is again will remain on the top side, followed by this O PMB, or the group present will be remain as it is. So in this case, you can see here the hydroxy group present, which is this hydroxy group, which is become beta. This methyl already it was the beta position. Now this methyl will be anti to this hydroxy group, right? Because attack takes place from the backside. So this will be backside. So this is what product we get. And upon hydrolysis, what happen? So if you just do the hydrolysis, what happen? We get this product basically. Yeah, this is the product we get here. So up to here, it was the imine. So once we do the hydrolysis of this imine, so what we get? We get the aldehyde back. So it was the aldehyde. So I just write the proton here. Okay, so this is what we get. So this is one simple example. So you can see in this case, this acts as our auxiliary, which induce the enantioselectivity in the reaction, right? So any doubt in this one? All right. So we'll take another example. So which involve similar sort of selectivity. So these are the two examples. So which involve similar chemistry. So we have the aldehyde and one ketone, and the catalyst here is the same proline based catalyst. So this is the catalyst. So what happened this with this catalyst? So this catalyst basically forms the imine in the similar fashion with the aldehyde and sorry with the ketone, and further it forms the enolate as in the mentioned in the earlier step. So it forms the imine followed by the enolate and attack this enolate attacks on this aldehyde present. So once it attacks, so we get some sort of selectivity because of this auxiliary part attached. We are attaching to the this ketone. So you can see in this example particularly, we get the anti to syn ratio 95 as to 5. So this basically enantiomeric excess here mentioned right now. Forget about this enantiomeric excess. So this terms anyway. So we are getting in this case the anti product as a major product. However, in the sorry in the another example also you can see. So this is the cyclohexanone and this aldehyde. So this catalyst particularly from the imine followed by enamine, and this enamine attacks on this aldehyde part. So we get this anti-product. So this anti-product we are getting as a major product, right? So this is what this how we can basically induce the enantiomer selectivity in the product. So do you guys are so I will take more examples on the similar fashion. So it will be easy for you understand this concept further more detail. So I will also put the reaction mechanism for this imine, enamine, this sort of mechanism, and which involve the some transition state which govern the stereochemistry. So this is the mechanism. So you can refer this mechanism to solve similar problems. So not only in this retrosynthesis course, but also for the your other general organic chemistry. So here, what happened this enamine mechanism? The ketone react with this amine. It form this sort of imine intermediate. So this natron is now tetravalent, so it get positive charge. So what happened? This H2O get eliminated, and we forget the enamine. So this was the imine. This is the enamine. Now what happened? This enamine react with the further. So in this case, aldehyde, further aldehyde. So in this case, CH3 C double bond OH. So this aldehyde and this enamine, so it forms such similar this type of transition state, chair-like transition state, as you can see here. So this transition state is getting formed, and this is then convert into this type of anti-addition product. So you can see this is the product we are getting in the product. When we have any stereochemistry present earlier in the product, in as you seen in the earlier example, this example, so we have already one uh, methyl group present here. So in that case, what happened? So as earlier also discussed, so the attack on the opposite side to this methyl group, so or the that group takes place. So in this case, attack takes place on the opposite side of this methyl group or the bulkier group, and we get the accordingly the product information. So you can refer this mechanism for to solve this type of problems. Like this is all about the asymmetric synthesis, and now we'll see some problems. So this is the another problem. You can refer this one. Right. So this is another two examples. So you can see in the retrosynthesis of these two molecules, what we did. So we have this target molecule, and you can see this target molecule, how where we can how to do retrosynthesis of the target molecule. So basically, this target molecule might be comes from. So here there will be a disconnection. So it might be come from this part, so which involve this acid and NH2 group, sorry, ester and amine group, and further another acid group from the another part. So basically, this is example of chiral pool and chiral pool synthesis. So from these two chiral centers, we just use this to substrate in the pure form. So we get our target molecule with the same pure enantiomeric form. So we get in our target molecule also the same chiral centers induced. So this is chiral pool approach. Another here, the synthesis involve the chiral pool auxiliaries. So basically, acyl chloride added the similar manner, the same chiral auxiliary which involve this some steric bulk kinase. So here, this example in this case, the exam what we have did here, Al2, sorry, ethyl, diethyl, uh, aluminum chloride. So this is just kind of Lewis acid. So we have the diene, sorry, this is diene and the dienophile. This is diol cellular reaction basically. The acid, sorry, Lewis acid catalyzed. So this Diels-Alder reaction get enantioselectivity selectivity because of this steric bulkiness present in this diene molecule, right? Sorry, this dienophile molecule. So you can see because of this steric bulk, this entire group attack in the endo fashion, not the exo. So we get this product as a major product. So another product, what is the possible another product was in this case, the another possible product will be this entire group might be attached in this fashion, but that's not the happen in this example, particularly because of this steric bulkinase present in this auxiliary part. And later, last part was the just removal of this auxiliary. So this is another example. So you can see in the Diel-Solder reaction also we induce the some sort of selectivity, enantioselectivity selectivity. So any doubt in this one? So do you know how the Diel-Solder reaction works? So also, there are some examples, particularly which involve the some reagent actually, and so you may aware about the sharp place epoxidation reaction. So this is the example of the same sharp place epoxidation. So basically, what we have diethyl tartrate in the form of plus diethyl tartrate or minus diethyl tartrate. So if you just Google it, the structure of this diethyl tartrate, you will get to know. So this diethyl tartrate is basically induce the epoxidation formation in this reaction. So you can see here, this okay, here already the structure of diethyl tartrate is given. So this is basically plus diethyl tartrate, and this is the minus diethyl tartrate, right? So what happened? So we have the if we have the alkene which involve alpha hydroxide. So in presence of the titanium isopropoxide, uh, third butyl hydrogen peroxide and plus diethyl tartrate, we get the epoxide, right? Epoxide like this. So this oxygen directing downward. So we get, so if you look at assign the stereochemistry here, so this is one, two, three. This is the basically R. We get the R epoxide. But if we use the minus diethyl tartrate, what happened? So we get the, sorry, it's earlier it, so this is the R actually, and this is the S. So we get the R diethyl, sorry, R epoxide. So the epoxide with the hydroxy group, sorry, oxygen atom directing upward. So this is basically the Sharpless asymmetric epoxidation, and the Nobel Prize in 2001 got for this catalytic asymmetric oxidation reaction. So in the earlier examples, what we did, example we have studied, we can do the resolution, further we can do the chiral pool, or we can do the chiral auxiliary. Other than this, we can also use the some catalyst which induce the uh, initial selective formation of the product. So this is the example from that one. And also there are other some reactions for the asymmetric. So just for your homework, I will give some examples or the names for these reactions. So just have a look at these examples, so it will be easy for you to understand the more this asymmetric topic in the more detail. So asymmetric aldol condensation also there. So asymmetric dialsulfide reaction also there. Further asymmetric dihydroxylation of the amino. Asymmetric dihydroxylation, also asymmetric amino hydroxylation examples are also there. Further asymmetric reduction. So we may heard about come across about the CBS reduction. So that's the asymmetric reduction example. Further asymmetric hydrogen transfer and asymmetric hydrox hydroxylation reaction and asymmetric reaction for the synthesis of the natural product. So these are some topics you can have a look and uh, have a overlook. So for this one, I will give some of the uh, I will upload the PDF for the some of the books, so you can refer that one. Mainly the I think the one book I just I didn't have to check whether I have the that in the form of PDF or not. So if I have Caruthar, yeah. So you can refer the Caruthar. That book particularly contain several examples on this sort of asymmetric synthesis. So we'll take few more examples, and we'll stop here for today. So from next next session onward, what we'll do, we'll take the mixed examples, which particularly involve the uh, all sort of problems, whether it is asymmetric, whether it is reagent-based problem, retrosynthesis, or whether it is some sort of asymmetric synthesis based. So all type of problems that I will take from the next video onward. So I will give you some problems here, so you can work on that one. Maybe you can play with the retrosynthesis for these molecules. So this is the one. You can do the retrosynthesis for this molecule. Further, this is the another example. Uh, Work on the retrosynthesis of this example as well. This is the third example. This example do not involve any asymmetric synthesis. They are just normal synthesis. We just work on this one. And if you want to do the asymmetric synthesis, what you can do, I will introduce. So in the same example, later I will just take it on the another slide here. So do the retrosynthesis. So for this one, we do not involve asymmetric synthesis. The other one, what you can do, just try to synthesize the molecule in this fashion, whether on this type or another. So this one, right? So this one. So basically, what I did here, I just mentioned the beta hydroxy groups. So hydroxy group directing upward. The similar manner, I think here you cannot do anything. Here, so you can try actually. So can you make the chirality on this molecule? So like this, and also the same example here also. Let's say this is directing upward. So like this. So how you can do the chiral synthesis for this one? So that, and in this case, so this selectively, this E isomer, not the Z. So E, you can do E as well as you can do the Z separately and the racemic also. So basically each question involve the three type of synthesis. One is the normal synthesis, do not involve the chirality. The second one is the particularly for the S isomer or particularly for the R isomer. The same manner S or R or RS racemic mixture. So these three type of retrocesses you can work out in that one. So we'll stop here for today and we'll see some more example in the next class.